Hello everyone, welcome to our channel Adivigyan Engineering. Today our topic is improper integrals. So let us first see what is improper integral. So let us say we have a definite integration a to b fx dx. Now this integration is called an improper integral or an infinite integral when either a or b or both are infinite or fx is unbounded in the interval a to b. So if a or b or both are infinite, or there may be another option that fx may be unbounded or fx is unbounded in the interval x a to b, then we can say this integral is an improper integral. Okay, now see, we can prove that if a function fx is unbounded in the closed interval a comma b, or you can say a to b, then there exists at least one point c in this interval. In this interval there will be a point c such that in the neighborhood of c fx is not bounded. This point c is called point of infinite discontinuity of the function fx, or we can say that that point c is a point of singularity of this integral. Now if we see some example, let us say we have integral of the form 0 to infinity dx by x square, or integral minus infinity to infinity dx by 1 plus x square. These are improper integral. Okay, I am writing it as II, improper integral, because here c b is infinite, and if we talk about the second example, here a and b both are infinite, so these are infinite integral. Now see, if we talk about this integral, integration 0 to 1 dx by x, this is also an improper integral. Why? Because here fx is unbounded, right? Fx is 1 by x, so we can say this is also an improper integral, because we can see that 1 by x is tends to infinity at x equals to 0. So this is also an example of improper integral. Now if we take another example, let us say we have integration 0 to 2 dx by square root of 2 minus x. This is also an example of improper integral, because if you put x is 2, then 1 by 2 minus 2 is 0, that is infinite, right? So here function fx is infinite. So you can say that this integration is also an improper integral, as we can see that 1 by square root of 2 minus x tends to infinity at x tends to 2. Now if we take another example, let us see we have minus 3 to 3 dx by x into 1 plus x. This example, this is also an improper integral, because initially we can see that uh, this is finite, lower limit is finite, upper limit is finite, and this is also finite. But if we take x values as 0 or minus 1, we can see that If we put 0, then 1 by 0 will be infinite, and if we put minus 1, 1 minus 1, 0, then that in that case also this function fx, that is 1 by x into 1 plus x, is also infinite. So this is also an improper integral. Okay. Now from these examples we can say that there are two types of improper integrals. Okay. Now this first example is the type 1 of improper integral. Okay. So we can say that the first type of improper integral, first type of improper integral is of the form integration minus infinity to infinity fx dx. Okay. Now if we see the examples 2, 3 and 4, these are example of second type of improper integral. Okay, these are example of second type of improper integral. So we can say that second type of improper integral is of the form integration a to b fx dx. Okay, where fx is not bounded, where fx is not bounded at x equals to c, where c lies between a to b, close interval a to b. Now let us see the techniques to evaluate type 1 and type 2 of improper integral. So first one is evaluation of improper integral of first type of first type. So here in this first type we have two types actually lies in first type. So let's talk about type 1. So let a function fx is bounded. Here we assume that fx is bounded, okay, and integrable in the domain a to x to capital X, that is small x lies between a to capital X. Okay, for all capital X belong greater than alpha. So then we can say that integration a to infinity fx dx is defined as limit x tends to infinity integration a to infinity fx dx, provided this limit exists. So you have to know this, provided the limit exists. Okay, so we can say that integration a to infinity fx dx is actually limit. We are finding the limiting value at x tends to infinity, right? So limit x tends to infinity integration a to x. Okay, this should be, made a mistake here, this should be a to x. Okay, this should be a to x, a to capital X. Okay, limit x tends to infinity a to capital X fx dx. That's how you have to solve the improper integral of the first type, where upper limit is infinite. Okay, So what you have to do, you have to take the limiting value at x tends to infinite and evaluate the integration from a to capital X fx dx. So let's take one example. Let us say we have to evaluate this integration from 0 to infinite dx by 1 plus x square. Here we can see that it is an improper integral because our limit is infinite. So what we have to do? We have to take the limiting value, that is limit capital X tends to infinity integration 0 to capital X 1 by 1 plus x square dx. Now simply solve this integral. So it will be limit x tends to infinity, and we know 1 by a square plus x square is tan inverse x by a. So here a is 1. So it will be tan inverse of x from 0 to capital X, and if you put the limits, the upper limit and lower limit, so limit x tends to infinity tan inverse of capital X minus tan inverse of 0. Now if you put x tends to infinity here, then it will be tan inverse infinity is pi by 2. So it will be pi by 2 minus tan inverse 0 is 0. So it will be pi by 2. So answer is pi by 2. Now let us see our second type, that is type 2. Okay. Now here also we assume that the function fx is bounded and integrable. Okay. In x lies between capital X to b for every x less than b. Okay, here capital X is always less than b. Here what we have to do, we have to take the limiting value of lower limit. So limit capital X tends to minus infinity integration capital X to b fx dx. That should exist finitely. That should exist finitely. Okay. So then this proper integral, then this improper integral. Let us say we have the improper integral as minus infinity to b fx dx. So here we can see that lower limit of the definite integration is infinite. So what we have to do? We have to take the limiting value, that is limit x tends to minus infinity integration capital X to b f of x dx. Okay. Now let's see one example to clear this. So let us take one example. Let us say we have to evaluate this integration minus infinity to 0 e to the power x dx. Okay. So clearly we can see that is an infinite improper integral, and where lower limit is infinite. So you have to take limit x tends to minus infinity integration x to 0, here upper limit is 0 e to the power x dx. So now simply evaluate this integral and put the limit, you will get the answer. So limit x tends to minus infinity integration e to the power x is e to the power x. So it will be e to the power x from capital X to 0. So then it is limit x tends to minus infinity If you put upper limit, then it will be e to the power 0. If you put lower limit, minus e to the power capital X. E to the power something to the power 0 is 1, so it will be 1, and this is e to the power minus infinity. Okay, so e to the power minus infinity means 1 by e to the power infinity. E is 2.414. 2.414 to the power infinity means infinity. 1 by infinity is 0. So this value is 0. So our answer is 1. So I think you got the point. Now here in the uh, first type we have another form, that is type 3. So let us see that type 3. Now see, in the first type we have seen that their upper limit is infinite. In the second type we have seen that our lower limit is infinite. So there may be some cases where both of the limits are infinite. So that falls under type 3. So let us take another integration, that is minus infinity to infinity fx dx. Now let us see. Let us say that c lies between minus infinity to infinity. So we can break this limit in the interval c. So this would be minus infinity to c f of x dx plus integration c to infinity f of x dx. Now this is type 2 and this is your type 1. So simply you have to apply both the types here. So limit, let us say this is your x1 tends to minus infinity. So then integration would be integration x1 to c f of x dx plus limit, let us say this integration the infinite value is x2. So x2 is plus infinity integration c to x2 fx dx. So this is none other than the mixture of type 1 and type 2. So let us see one example to clarify this logic. Let us say we have to evaluate this integration minus infinity to infinity x by x to the power 4 plus 1 dx. So we can clearly see that this is an improper integral where lower limit and upper limit both are infinite. Okay, so then we have to break this within an intermediate point c. So it would be minus infinity to c x by x to the power 4 plus 1 dx plus integration c to infinity x by x to the power 4 plus 1 dx. Now we have to apply type 1 and type 2. This is your type 2, this is your type 1. So here we can see, we can say that limit x1 tends to minus infinity integration x1 to c, that is x by x to the power 4 plus 1 dx plus limit x2 tends to infinity integration c to x2 x by x to the power 4 plus 1 dx. Now what we can uh, see here, that we can actually uh, take the take the substitution method, or we know that limit this is x1 tends to minus infinity. See, if we write this x in the form d of x square, so see what is the differentiation of x square, that is 2x, but we don't have 2 here, so we have to multiply by half integration x1 to c, and this would be d of x square, right? Because we have taken half, so we can write x dx as d of x square. Now this thing you can write it as x square square plus 1. Similarly, apply the same method here. Limit x2 tends to infinity, half of integration c to x2. This is d of x square by x square plus 1. Now see, we know that 1 by x square plus 1 is your tan inverse x, or x square plus a square is tan inverse x by a, right? So here x is your x square, because see, if we have dx by 1 plus x square, or we can say a square plus x square, this formula is tan inverse of x by a. So if you notice here, when we have x within d, then we have x square. So when we have in place of x we have x square, then in the denominator we should have x as x square, right? Now if you compare this, here in place of x we have x square, so here in the denominator in place of x we have x square. So these two formula are actually same. So this would be limit x1 tends to minus infinity, half of this is tan inverse x by a. So x is your x square by 1 is same thing, right? From the limit is x1 to c, plus this would be half limit, this is x2 tends to infinity, x2 tends to infinity, and this would be similar thing, tan inverse of x, tan inverse of x, that is x square, c to x2. Now put the limits. So this will be limit x1 tends to minus infinity, take the half outside the limit because it is constant. So it would be tan inverse of c, tan inverse of c square minus tan inverse of x1, that should be capital X1 square, plus half of limit, which is x2 tends to infinity. This should be tan inverse of capital X2 square minus tan inverse of c square. Okay. Now if you put minus infinity here, so it would be half of limit, half of limit, we have to put the limit here, so don't write it. So if you put in place of x1 minus infinity, then it will be tan inverse of c square, and when we put x1 as minus infinity square, it will be plus infinity, so it would be tan inverse c square minus tan inverse infinity, that is pi by 2, plus half of limit, sorry, I have again write it down. This would be half of tan inverse of infinity square is infinity, so tan inverse infinity is pi by 2 minus tan inverse c square. So this half of tan inverse c square and plus half of tan inverse c square, and this is minus half of tan inverse c square, is will cancel out, and this is half of minus half of pi by 2, and this is plus half of pi by 2, so it is 0. Okay, have you got the point? Now moving forward to our evaluation of improper integral of second type. Evaluation of improper integral of second type. Okay, So let us see. So let within this we have again three types. So let us talk about type 1 first. Let A be the only point of infinite discontinuity. Let A be the only point of infinite discontinuity. Infinite discontinuity of the function f of x. Then the improper integral integration a to b fx dx is defined as, then the improper integral integration a to b fx dx is defined as is defined as limit epsilon tends to 0 plus integration a plus epsilon to b fx dx, provided this limit exists. Okay, so we can say that integration a to b fx dx is limit epsilon tends to 0 plus integration a plus epsilon to b fx dx. Okay, so from this it is clear that here we have the infinite discontinuity at the lower limit, right? So we have add a point, a small positive quantity epsilon, to make the improper integral in proper form. If we take one example to understand this, so let us say we have to evaluate integration 0 to 4 dx by root x. Okay, so here you can see that at lower limit, that is if you put 0 here, so 1 by 0 is infinite. So here we have only one point of discontinuity, that is 0, and we have written it down, right? If a be the only point of infinite discontinuity, so you should have only one point of infinite discontinuity. So from our knowledge we can say that this integration we can write it in the form limit epsilon tends to 0 plus, we have to take a small positive quantity, that is a plus epsilon, that is we can say 0 plus epsilon to 4 dx by root x. Now simply evaluate this, you will get the answer. Limit epsilon tends to 0 plus, and it would be x to the power minus half. So you know that integration x to the power n dx, the formula is x to the power n plus 1 by n plus 1. Okay, now this is x to the power minus half, so it would be x to the power minus half plus 1 by minus half plus 1 from limit epsilon to 4. 0 plus epsilon is epsilon, right? So we can say limit epsilon tends to 0 plus, this is x to the power minus half plus 1, that is plus half, that is square root of x, and this is plus half, so it would be 1 by 1 by 2, that is 2 twice root x from epsilon to 4. Now put the values. Limit epsilon tends to 0 plus, if you put 4 you will get 2 multiplied by 2 is 4 minus 2 root epsilon. Epsilon is 0 plus, that means it will be 0, so answer is 4. Now let's talk about type 2. Let's talk about type 2. So I think you got the point. Here upper limit will be unbounded. Okay, and let us say here b is the only point of discontinuity, so we can write integration a to b fx dx. We can write this. Remember, here b is the only point of discontinuity. So if the lower limit is unbounded, we have to add a positive quantity. If upper limit is unbounded, then we have to minus negative quantity, a small positive quantity. We have to subtract a small positive quantity from the upper limit. So we can write this limit. If you have a point of discontinuity in the upper limit, we can write it as limit epsilon tends to 0 plus integration a to b minus epsilon f of x dx. Okay, now let's take one example so that you can realize how you can solve this type of problem. So let us say we have integration 1 to 2, we have to evaluate 1 to 2 dx by square root of 2 minus x. So here you can see that if you put 2 here, 1 by 2 minus 2, that is 0, that will be infinite. So we have point of discontinuity at upper limit. So we can write this integration as limit epsilon tends to 0 plus integration 1 to, here discontinuity at upper limit, so we have to subtract this small positive quantity. So it would be 2 minus epsilon dx by square root of 2 minus x. Now simply solve this. Okay, here we can apply substitution method. In that case, we have to change this limit, or we can simply say that this limit is limit epsilon tends to 0 plus, it will be minus 2 square root of 2 minus x 1 to 2 minus epsilon. See, here what we have done, that we have applied that formula 1 by root under of square root of 2 minus x. So we can write this as 2 minus x to the power minus half. Now simply apply x to the power n formula, that is x to the power n plus 1 by n plus 1. So x to the power minus half plus 1 by minus half plus 1. So you will get twice square root of 2 minus x, right? As we have minus 1 with before x, so you have to divide by minus 1. If you have here 2x, then you have to divide by 2. If you have here minus 4x, then you have to divide this thing by minus 4. Okay, that's how you have to remember this type of integration. Or you can apply simply the substitution method. So let me solve the limit first, then I will show how to solve this type of integration by substitution method. So if you put upper limit and lower limit, you will get limit epsilon tends to 0 plus. So if you take minus 2 outside, it will be 2 minus of 2 minus, and this is sigma, so epsilon, so that is minus minus plus, so it will be epsilon. Okay, and if you put 1 here, you will get 2 minus 1 is 1, so you will get minus 1. Now if you put epsilon tends to 0 plus, then that would be, this would be 0, and minus 2 into minus 1, that is plus 2. This is your answer. So let us see, if you are not habituated with this type of integration, so let 2 minus x as t, then differentiate both the side with respect to x, then differentiation of 2 is 0 and differentiation of minus x is minus dx. So this would be dt. So dx would be minus dt. So we can say now in the definite integral we have to change the limit also. So when x tends to 1, when x tends to 1, so if you put 1 here, t tends to 1, no problem. When x tends to 2 minus epsilon, then this x tends to 2 minus epsilon, that is 2 minus 2 minus plus epsilon. So then t tends to epsilon here. So our limit is limit epsilon tends to 0 plus integration lower limit is 1, upper limit is epsilon. So 1 to epsilon, and this would be dx is minus dt. Sorry, dx is minus dt, so it will be minus dt by root t. Okay, now solve this, you will get the same answer as we got. Now let us see our type 3. So I think you got the point here, that in type 3 we have to apply both type 1 and both type 2. So integration a to b, if there is a discontinuity at a and discontinuity at b, then what we have to take, we have to take a point between a and b where c gives the finite value. So it would be integration a to c fx dx plus integration c to b fx dx. Okay, now here we have point of discontinuity at uh, a and discontinuity at b. So this is your type 1 and this is your type 2. Okay, now you can merge this. Limit epsilon 1, let us say, tends to 0 plus integration a plus epsilon 1 to c fx dx plus, let us say, limit epsilon 2 tends to 0 plus integration c to b minus epsilon 2 fx dx. Okay, now let us see one example to understand this thing very clearly. Let us say we have integration, we have to evaluate integration 0 to 1 dx by square root of x into 1 minus x. Now here we can see clearly that if we put 0, this will be infinite. If we put 1, this will be infinite. So we have point of discontinuity at 0 and 1. Right, this is point of infinite discontinuity. So we can write, let us assume that we have a point half, 0 to half, because if you put here the value half in place of x, then it will give a positive quantity. Okay, so it will be 0 to half dx by square root of x into 1 minus x and plus integration half to 1 dx by square root of x into 1 minus x. Okay, now apply type 1 and type 2 here. So if we apply type 1, limit epsilon 1 tends to 0 plus, we have point of discontinuity at lower limit, so we have to add positive quantity. So it will be 0 plus epsilon 1 to half dx by, now we can write this as, okay, this is square root of x into 1 minus x. So we can say that this is x minus x square. First take minus common, so it will be x square minus x, then it would be x square minus, we can say that 2 a is x, b we have to take half because 2 to cancel out, we will have x. So our b is half. So plus half square, we have taken this term extra, so you have to subtract this term. So it will be minus, it is a square minus 2ab plus b square. So it would be a minus b whole square. This is minus half square. So it would be square root of, if you multiply it by minus, it would be half square minus x minus half square. Okay. Now you can write this half square minus x minus half square plus limit, let us say this is point of discontinuity at 1, right? So we have to take another epsilon. Let us say this is epsilon 2 tends to 0 plus integration half to 1 minus epsilon 2. For upper bound, we have to subtract. For lower bound, we have to add. So it will be dx by same thing, square root of half square minus x minus half square. Now here we have to put apply the formula 1 by root under a square minus x square. So it will be 1 by a sin inverse x by a, right? This is our formula. So we can say that limit epsilon 1 tends to 0 plus, this would be 1 by a, that is 1 by 1 by 2, that is 2. This is sin inverse x by a only. Okay, sin inverse x by a. Sorry, 1 by root under a square minus x square is sin inverse x by a. So it should be sin inverse x by a. Here x is x minus half, a is half. Okay, it is only sin inverse x by a. Now this is the limit is from 0 plus, sorry, 0 plus epsilon to half plus limit epsilon 2 tends to 0, sin inverse x by a. So sin inverse x minus half by half from half to 1 minus epsilon 2. Now if we simplify, limit epsilon 1 tends to 0 plus, this would be sin inverse of 2x minus 1 by 2, and this 2 and this 2 cancel out, so it will be only sin inverse of 2x minus 1 from epsilon to half plus, this is limit epsilon 2 tends to 0 plus. Okay, this is also sin inverse 2x minus 1 from the limit half to 1 minus epsilon 2. Okay, now put the limit. This is sin inverse, if we put upper limit here, so 2 into half is 1, 1 minus 1 is 0, sin inverse 0 is 0, minus lower limit, so it will be minus sin inverse of 2 epsilon minus 1, limit epsilon 1 tends to 0 plus. Here you will have minus because upper limit minus lower limit. Similarly here you will have plus limit epsilon 2 tends to 0 plus. If you put 1 minus epsilon 2 here in place of 2x, okay, you will get 2 minus 2 epsilon 2 minus 1, that is 1 minus 2 epsilon 2, sin inverse 1 minus 2 epsilon 2. and if we put lower limit minus lower limit, so 2 multiplied by half, that is 1 minus 1 0, sin inverse 0 is 0. Now if we put epsilon tends to 0 here, so it would be sin inverse of minus 1, and sin inverse of minus 1 is minus sin inverse of 1, sin inverse of 1 is pi by 2, so we'll get pi by 2. Similarly, if you put 0 here, sin inverse 1 is pi by 2, so it will be pi. So answer is pi. Now here we have another type of uh, let us say we have type 4 here. Okay, in this type, what we have to do, let us say in between the points there is a discontinuity that may also occur, right? Let us say type 4. Here let us say a to b fx dx. This function is continuous, this uh, a is bounded, p is bounded, but in between one point, let us say at the point c, we have a point of infinite discontinuity. So at this case, in this case we can say that this is limit epsilon 1 tends to 0 plus integration a to c minus epsilon fx dx plus limit because we have infinite discontinuity at the point c, so this is the upper bound, upper limit, so we have to subtract, right? So limit epsilon 2 tends to 0 plus integration, this should be c plus epsilon 2 b fx dx. Okay, because see, we know that integration a to b fx dx, we can write it as integration a to c fx dx plus integration c to b fx dx. Here in this case there is a point of discontinuity, infinite discontinuity at this point, right? That's why we assumed here, we write it here the type 1 and type 2 in the format type 1 and type 2. Okay, now here you have to note that here both of these limit should exist. Okay, so another thing you have to note it here that uh, when we take epsilon equals to epsilon 2, if we take epsilon and epsilon 2 equal, then we can say our integral would be a to b fx dx would be limit epsilon 1 tends to 0 plus integration a to c minus epsilon 1 fx dx plus integration c plus epsilon 1 to b fx dx, because here we have assumed that epsilon and epsilon 2 are same. Now this whole thing is called Cauchy principal value. Okay, this is Cauchy principal value. This is known as Cauchy principal value of the integral. Okay, uh, sometimes this Cauchy principal of the integral exist, whereas the general definition of the integral does not exist. Now let us take some question. Let us see first, let us understand this type 4, then we will move forward to solve 2 to 3 questions, then we will end up this session. Let us say we have to evaluate this integral from -1 to 1 dx by x cube, right? Here everything looks good, but we know there is a point 0 in between -1 and +1. So if we put 0 here, 1 by 0 is infinite. So there is a point of discontinuity at 0, infinite discontinuity at x equals to 0. So if we take fx is 1 by x cube, we can say this function has infinite discontinuity, infinite discontinuity at x equals to 0, right? So we can write this as -1 to 1 dx by x cube as integration -1 to 0 dx by x cube plus integration 0 to 1 dx by x cube. So here we can say that limit epsilon 1 tends to 0 plus, here we have infinite discontinuity at upper limit, so we have to subtract. So integration -1 to 0 minus epsilon 1 dx by x cube plus limit epsilon 2 tends to 0 plus integration 0 plus epsilon to 1 dx by x cube. Okay, now apply the formula x to the power, this is x to the power -3, so x to the -3 plus 1 by -3 plus 1. This will be limit epsilon 1 tends to 0 plus, this would be minus 1 by 2x square -1 to minus epsilon 1 plus limit epsilon 2 tends to 0 plus minus 1 by 2x square. This is epsilon to 1. Okay, so this would be limit epsilon 1 tends to 0 plus. If you put epsilon here, so it would be minus 1 by 2 epsilon 1 square, and upper limit minus lower limit, so minus minus would be plus, and it would be half. Okay, so plus limit epsilon 2 tends to 0 plus. If you put upper limit here, so it will be upper limit is minus 1 by 2 minus minus plus, it will be 1 by 2 epsilon 2 square. Now from this we can clearly see that limit epsilon 1 tends to 0 plus 1 by 2 epsilon 1 square, this limit do not exist, right? And similarly limit epsilon 2 tends to 0 plus 1 by epsilon 2 square also does not exist, because 1 by 0 plus, that means 1 by 0 you can take, it will be infinite and it will be infinite also. So we can say that integration -1 to 1 dx by x cube does not exist, does not exist. But here we, if we take Cauchy principal value, that means where epsilon 1 and epsilon 2 are same. So let us take when epsilon 1 equals to epsilon 2. Okay, so if we take this integration -1 to 1 dx by x cube, so it will be limit epsilon 1 tends to 0 plus, this limit 0 plus, this is half minus 1 by 2 epsilon 1 square, so half minus 1 by 2 epsilon 1 square 2 plus limit, this is epsilon 2 and epsilon 1 are same, so we can write it as epsilon 1 tends to 0 plus, this is minus half plus 1 by 2 epsilon 2 square. Okay, now putting the limit, we can say that this is your, if you take limit epsilon 1 tends to 0 plus common, then it will be half minus 1 by 2 epsilon 1 square plus of minus, that is minus half, that is minus half minus half plus 1 by 2 epsilon 2 square. So this will cancel out, half minus half is 0. Okay, so you can say that integration minus 1 to 1 dx by x cube exists in the Cauchy principal value, Cauchy principal value sense, right? But not in general sense. But not in general sense. General sense is this, right? This is our general sense. When epsilon and epsilon 2 are different. But in the Cauchy principal value sense, this is epsilon 1 and epsilon 2 are equal. Only then it exists. Okay. So you have to note that when the appropriate limit exists finitely, an improper integral is said to be convergent. In other words, when the appropriate limits uh, you can say fail to exist or tend to infinity, an improper integral is said to be non-convergent. So you have to remember this. Okay, when appropriate limits exist finitely, an improper integral is said to be convergent. Okay, and if fails to exist, then it tends to infinity or tends to infinity, then that improper integral is said to be non-convergent. Okay, so let us say our let us see our next topic, which is some standard improper integrals. We have our first improper integral type as A. Let us say this is A. Now we want to check the convergence of integration A to infinity dx by x to the power n, where A is greater than 0. Now clearly we can see that this integration is improper integral of first type, right? So you have to apply the first type method and you will get it here. If you take okay, let's solve this. This is integration A to infinity dx by x to the power n, right? So in the upper limit we have infinite point of discontinuity, so we can take limit x tends to infinity integration A to capital X dx by x to the power n. So it will be limit x tends to infinity, x to the power, this is x to the minus n, so x to the power minus n plus 1 by minus n plus 1 from a to x. Okay, so this will be limit x tends to infinity, and if you take this common 1 by 1 minus n, then this would be a to the power minus n plus 1. So this is 1 by a to the power n minus 1, you can say, if you take minus common from this. And uh, from the lower limit, okay, let's solve this step by step so that you do not make any mistake. If we put upper limit, it will be capital X to the power minus n plus 1 minus lower limit, that is a to the power minus n plus 1. Now if you take minus 1 minus common, so then it will be 1 minus n minus 1. Okay, it will be n minus 1. Now you can say that this is your limit x tends to infinity, and if you take minus from this and minus from this, then it will be 1 by n minus 1, and this will come in the first. So it will be 1, it will be a to the power minus n plus 1, and if you take minus common from this, so it will be 1 n minus 1. So ultimately it will be a to the power n minus 1. Okay, minus, this is x to the power minus n plus 1. If you take minus common from this, it will be 1 by x to the power n minus 1. Okay, now from this you can observe that when n is greater than 1, you will have this value n minus 1 into a to the power n minus 1, and when this n value is less than 1, then it will be infinite. Okay, but when n equals to 1, if we say when n equals to 1, okay, see, when n is greater than 1, then this will give a positive value. Now when n is greater than 1, it will be a positive value. 1 by infinity to the power positive, that means it will be 0. So when n is greater than 1, it will be 1 by n minus 1 into a to the power n minus 1. And when n is less than 1, let us say n is less than 1, so it will be x to the power minus something. So infinity to the power minus something. Infinity to the power minus means 1 by infinity. So it will be infinite, right? Infinite minus some positive quantity, so it will be infinite. And when n equals to 1 here, so if you see, when n equals to 1, it will be a to infinity 1 by x only, right? So a to infinity dx by x to the power n would be integration a to infinity dx by x. Okay, now if you put limit x tends to infinity integration a to x dx by x. Now 1 by x is log of x. So limit x tends to infinity, this is log of x, okay, from a to capital X. This is capital X. Okay, now it will be log of capital X minus log of a, that is log a minus log b, that is log of a by b. So you can say limit x tends to infinity log of capital X by a. Now log of infinity is infinity, so it will give infinite value. Okay, so from this discussion we can see that this integration is convergent when n greater than 1 only. You will get a positive value, you will get a value, right? But when less than 1, this is infinite, and when equals to 1 also, this is infinite. So we can say that the given improper integral is convergent when n is greater than 1. Okay, now let's see some example. Integration 1 to infinity dx by root x. Tell me whether it is convergent or not convergent, and if it is not convergent, at which point it is not convergent. So we can see that this is our standard form from a to infinity dx by x to the power n. So a to infinity. So this is our first type. X to the power n. Here n is half, right? So half means n is less than 1, right? N is less than 1. So if n is less than 1, then it will be infinite. That means not convergent, right? It's very easy. Just what you have to do, you have to remember the types. So this is not convergent as n is half, which is less than 1, right? Let's take another example. Integration 2 to infinity dx by x cube. So if you take this example, see it is of the first type, dx by x to the power n is 3. So n is greater than 1, so that means it is convergent. So is convergent as n equals to 3, which is greater than 1. Now take another example. Integration 1/3 to infinity. This is dx by x. So this is x to the power n is 1. So we know that when n equals to 1, it will be not convergent. So is not convergent, is not convergent as n is equals to 1. Okay, so this is our A. Let's see B. So if we talk about B, convergence of integration a to b dx by x minus a to the power n, where n is greater than 0. So if we put a here, a minus a would be 0, 1 by 0 would be infinite. So we can say that here x equals to a is the only point of infinite discontinuity. Okay, infinite discontinuity. Now let's solve this problem. Okay, so every time you don't have to solve, I'm writing here the solution at which point it will be convergent and which point it will not be convergent. So this integration, that is integration a to b dx by x minus a to the power n, this will give minus 1 by n minus 1 into b minus a to the power n minus 1 when n is less than 1. This will give infinite when n is greater than 1, and this will give infinite when n is equals to 1. So you can say greater than equals to 1, it will give infinite, right? So this integral will only give will only be convergent when n is less than 1. Remember this. If we take example, see, tell me whether this point 2 to 3 dx by x minus 2 to the power 3 by 2, will it be convergent or not? See, this is the format, right? A to b dx by x minus a to the power n. So here n is a is 2, n is 3 by 2. And if you put 2 here, this is the only point of discontinuity, right? You have to remember the format. Here x equals to a is the only point of discontinuity, infinite discontinuity, right? So we know that in this format, when n less than 1, only then it will be convergent. But here n is 3 by 2, that is greater than 1, right? So it is not convergent. It is not convergent as n equals to 3 by 2, that is 1.5, which is greater than 1. Now let us take another example. If we say integration 1 to 2 dx by square root of x minus 1. So this is also in this format, right? If we put 1, it will be infinite. 1 minus 1, 0, 1 by 0, infinite. So here n is half. So it is convergent, right? It is convergent as n equals to half, which is less than 1. Now if we take another example, tell me minus 3 to 3 dx by x plus 3, whether it will be convergent or not. See here, x plus a to the power n, right? X minus a to the power n format. Here n is 1, so it will not be convergent. It is not convergent as n equals to 1. Okay. Now this is the convergence of integration a to b dx by x minus a to the power n, where you have point of infinite discontinuity at lower limit. Okay. Now let's see our C type, that is convergence of integration a to b dx by b minus x to the power n, where n is greater than 0. So this is b minus x to the power n format, where if you take b here, then see, if you put the upper limit here, then it will be 0, 1 by 0 is infinite. So here we can say here x equals to b is the only point of infinite discontinuity. Okay. So if you break this, you will get something like this: b minus x to the power n format. You will get this value as 1 by n minus 1 into b minus a to b minus a to the power n minus 1 when n is less than 1. This will be infinite when n is greater than or equals to 1. Okay. So let's take, so here, from here also we can see that this is convergent only when n is less than 1. let's take some example. Tell me whether this integral 1 to 2 dx by square root of 2 minus x is convergent or not convergent. This is in the same format, right? If you put here 2 upper limit, if you put upper limit here, it will be 1 by 0, that is infinite. So you have point of discontinuity at upper limit, and it is b minus x. Let's see, 2, 2, 2. So 2 minus x to the power n, n is half, which is less than 1. So it will be convergent. Okay. Now if we take another example, tell me whether this is convergent or not. Dx by 1 minus x square, if it is convergent or not. See, it is also in the same format, right? B minus x. So here b is 1, 1 minus x to the power n greater than 1. So it will be infinite. It is not convergent. Let us take another example. Let's say we have integration 0 to 1 dx by 1 minus x. It is also in the same format, b minus x to the power n. Here n is 1. So it is also not convergent. Okay. Now let's see 2 to 3 problems from this. So our question number 1 is, examine the convergence of the improper integral integration 0 to 2 dx by x into 2 minus x. Okay. So let's examine. So let us say here we have fx is 1 by x into 2 minus x. Okay. So it is clearly, we can see that if we put 0 here and 2 here, it will be infinite, right? So we can say x equals to 0 and 2 are the infinite discontinuity of f of x, right? So you can write this as, this implies 0 to 2, that is we have point of discontinuity at 0 lower limit and in the upper limit. So this would be dx by x into 2 minus x. We can write it as integration 0 to 1 dx by x into 2 minus x plus integration 1 to 2 dx by x into 2 minus x. Okay. Now apply our type 1 and type 2. Okay. Here in the lower limit we have point of discontinuity. Here in the upper limit we have point of discontinuity, and we have break it down in a interval point where it is continuous or it is convergent. So limit epsilon 1 tends to 0 plus integration 0 plus epsilon 1. We have seen all this type, right? So this will be, we can write it as, if we write this thing as 1 by x plus 1 by 2 minus x. So see, if you take LCM, it will be 2 minus x plus x. So x and x will cancel out. You will have 2 in the numerator. So we have to cancel that numerator. So we have divided by 2. Dx plus limit epsilon 2 tends to 0 plus integration 1 to 2 minus epsilon 2, half of 1 by x plus 1 by 2 minus x dx. Okay, so it will be, if we take half common, half in the outside, then it will be limit epsilon 1 tends to 0 plus 1 by x is log of x, so log of mod of x minus, this will be 2 minus x. See, if it is x minus 2, then it would be log of x minus 2, but if it is 2 minus x, then it will be log of 2 minus x, but here before that we have minus 1, so you have to divide it by minus 1. Okay, so this plus will be minus. Limit is from epsilon 1 to 1. Here also we can say the same thing. This is half limit epsilon 2 tends to 0 plus log of x minus log of 2 minus x. This is 1 to 2 minus epsilon 2. Okay, now put the limits. If you put it 1, log of 1 is 0, it will be log of epsilon. If you put 1 here, log of 1 will be 0, 2 minus 1 is 1, log of 1 is 0, and if you put epsilon here, it will be 2 minus epsilon, so it will be log of a minus log of b, but here for this we have taken upper limit minus lower limit, so minus minus will be plus, and this will be upper limit is 1 minus lower limit, that is minus log of epsilon 1, so it would be half of limit epsilon 1 tends to 0 plus log of minus log of epsilon 1 by 2 minus epsilon 1. Okay, plus half of limit epsilon 2 tends to 0 plus, it would be log of 2 minus epsilon 2 by epsilon 2. So we can see that this, if you put 0 here, log of 0 is not defined, and because we know for log of x to define, x should be greater than 0, x should be greater than 0, but if you put 0 plus log of 0, here will also log of infinity, log of infinity is also not defined. So this will be, we can say that limit epsilon 1 tends to 0 plus log of epsilon 1 by 2 minus epsilon 1, and limit epsilon 2 tends to 0 plus log of 2 minus epsilon 2 by epsilon 2 do not exist. Okay, these do not exist. So you can say this implies that the given improper integral is not convergent. Okay, this is not convergent. Now let us see another question so that your doubts will be more clear. Okay, let us see our next question. Our next question is, show that integration minus infinity to infinity x e to the power minus x square dx would be 0. Okay, so let's see the solution of this question. So here we can see that we have infinite discontinuity at lower and upper bounds, so we can write this integration as x e to the power minus x square dx as integration minus infinity to a x e to the power minus x square dx plus integration a to infinity x e to the power minus x square dx. So this is limit x1 tends to infinity minus infinity integration x1, because we have infinite discontinuous lower limit, here we have in the upper limit x1 to a. We can write this thing as e to the power minus x square, and x dx we can write it as d of x square. So here we will have 2x dx, but we do not have 2 here, so we have to divide it by 2 plus limit x2 tends to infinity half of integration a to x2 e to the power minus x square d of x square, right? So we can say half of limit x1 tends to minus infinity, and this integration would be, see, integration of e to the power x dx is e to the power x. So when you have x here, you have x here, then you will have x here. So if you have x square here, then you will have x square here, then you will have x square here. If you have minus x square here, then you will divide it by this thing by minus 1. Minus a x square, then you have to divide it by minus a. Okay. So this would be, this integration would be minus e to the power minus x square x1 to a plus this would be half of limit x2 tends to infinity. This will be minus e to the power minus x square from a to x2. So this will be half of, if you put limit here, it will be minus e to the power minus a square minus lower limit x1 square. So put the limits here, x1 to minus infinity minus e to the power minus a square plus e to the power minus x1 square, plus this would be half of limit x2 tends to infinity minus e to the power x2 square plus minus minus plus e to the power minus a square. Now if you evaluate this integral e to the power minus infinity, so e to the power minus infinity is 1 by e to the power infinity, 1 by e to the power infinity is 1 by infinity, that is 0. So it would be minus half e to the power minus a square, and if you put x2 tends to infinity here, it would be e to the power infinity, that is infinity, e to the power, sorry, there is minus, right? So e to the power minus infinity 1 by, that means 1 by e to the power infinity, that is 1 by infinity, that is 0. So it would be half of e to the power minus a square, it will give 0. Okay. Now let us say uh, let us see our last question in today's session, that is evaluate integration minus 1 to 1 dx by x square if possible. If not possible, find its principal value. Find its principal value if not possible. So Let's see the solution. Okay, see, this is a improper integral, right? Because we can clearly see that in between -1 to 1 there would be a value 0. 1 by 0 is infinite. Okay, so you can say that -1 to 1 dx by x square, that is limit epsilon tends to 0, integration -1 to 0 minus epsilon dx by x square, plus limit epsilon tends to, or you can say epsilon, if you take epsilon and this maybe epsilon prime tends to 0, integration 0 plus epsilon prime to 1 dx by x square. This would be x square, not dx square. Okay, so let's see, this is x to the power minus 2, that x to the power minus 2 plus 1 by minus 2 plus 1, so this would be minus 1 by x. So you can say limit epsilon tends to 0 minus 1 by x, this is minus 1 to minus epsilon, plus limit epsilon prime tends to 0 minus 1 by x, this is epsilon prime to 1. So if you put here, it would be limit epsilon tends to 0, it would be minus 1 by epsilon, that is plus epsilon. Okay, and this is upper limit minus lower limit, so minus minus plus, it would be 1. And here we have epsilon prime tends to 0, limit epsilon prime tends to 0, it would be minus 1 by 1, that is minus 1, and minus minus plus because minus lower limit, so this would be 1 by epsilon prime. So from this we can see that this limit does not exist and this limit also does not exist, because epsilon dash tends to 0 here, here epsilon tends to 0 here. Okay, so we can say that limit -1 to 1 dx by x square has no value. Okay, so we have to find out the principal value, right? So let's see the principal value. So its principal value would be, let us say principal value is p, this is -1 to 1 dx by x square. So this would be limit epsilon tends to 0. What do you have to do? We have to take epsilon 1 equals to epsilon 2, right? Cauchy formula. So -1 to 0 minus epsilon dx by x square plus integration 0 plus epsilon to 1 dx by x square. Okay, so this would be limit epsilon tends to 0, this would be 1 by epsilon minus 1 minus 1 minus 1 by epsilon. Proceed as same, you will get this. So here we can see that 1 plus 1 by epsilon, 1 by epsilon plus 1 by epsilon, that is 2 by epsilon. Okay, so limit epsilon tends to 0, this will be 2 by epsilon and this is minus 2. So from this Cauchy integral value we can see that again this value has, this do not exist, right? So ultimately we can say that integral has no principal value, no principal value also, right? In both the method, we can see that it do not have any, it do not exist, and it do not have any principal value. So I think you have understood this chapter. Okay. So if you like the video, please like, share, and subscribe. And tell me in the comment section in the next video what chapters you want me to upload. Okay, that's all for today. All the best and have a good day.